Hello, this is Jack Jackson. In this video, we're going to talk a little bit about Taylor polynomials. So recall in Calculus 1 how we often approximated a differentiable function with its tangent line and vice versa. These approximations are usually fairly good as long as the input is near the point of tangency. In other words, we can locally approximate a differentiable function with a first-degree polynomial function, the tangent line. In this section, we are going to generalize this result to locally approximate a function with an nth degree polynomial function, not just a first degree polynomial function. These approximating polynomial functions are called Taylor polynomials. Taylor polynomials give us one way to find approximate values of a function without a calculator, and they give us one method of writing code for a calculator or computer program to find approximate values for functions. So throughout this section, we're going to be using the following GeoGebra activity that I created to illustrate graphs of Taylor polynomials along with the graphs of the original functions. And there's the link there if you want to use that. So here is that setup here. So it's set up, you can enter in the formula for a function here. You can change the degree of the polynomial in here. You can change the center point here, which you can see graph right there by either the slider. I think you can also move this point here. Yeah, you can move this point here, or you can type in a number here. Okay, and we'll come back to this in just a minute or throughout this as we go through here. Okay, so let's start with the function. Say f of x is log of x. That's the one we actually just saw graphed. And we need an x value to start at, a center point. I'm going to call that center point A. In this case, A is 1. And then the point A, f of A, is on our graph. So in this case, that's 1 comma ln of 1, or 1, 0, is our point on the graph. And that's from the screen that you just saw, little applet there. And there's the point there, and there's the graph. Okay. Now the first question is, let's approximate this with different polynomial functions. And we want them to be very good. In fact, they want them to be perfect at the point a f of a, and they want it to be as close to the graph of the original function as possible nearby that point a f of a. So let's first back up something more basic than what we did earlier in Cal 1, and that's what if we could take a 0th degree polynomial approximation. Well, remember, a 0th degree polynomial is just a constant function. So the question could be rephrased as, what would be the best 0th degree polynomial function, in other words, a constant function or a horizontal line graph, that best approximates the graph of the function near a f of a? Well, with a constant function, the only thing that we can control is the choice of the constant, in other words, the height of the horizontal line, the y value, and the best we can do is make it be the same as the height of our point that we want. So the n equals 0 polynomial, p sub 0 of x, is just going to be f of a, which in this case is just 0. In this case, there's the axis there. So moving back to our original look to our formula here, if I move the a, let's see, first of all, there's the polynomial, and if I move this point around, I'm moving where that horizontal line is, but really all you can do is just match that particular horizontal line. Let's go back to a is 1 now. Now, if I want to be the best line that matches, not only can we match that point, but we can also match the slope there, and of course that gives us the tangent line. We've done this many times. The tangent line then in the slope-intercept form, which is point-slope form. That's what we want to use, is a point-slope form, because we want to center up at this point a f of a. Well, it's just f of a plus f prime of a times x minus a. So that goes through the point a, comma, f of a. Check it out. If a is x is a, this is factor 0, so that goes away, and you get f of a. So it does agree with the function at that point. And then what else? The slope is going to be the same. So if you take the derivative of this polynomial, you get 1, which is the derivative of the original function at that one point. And so the y value of the function agrees, and the derivative agrees at that point, and that gives you the tangent line. And of course, the tangent line is a much better approximation of the curve than the horizontal line is. they're both perfect and only perfect really at that one single point, but the horizontal line deviates from the curved graph here quite a bit very quickly, whereas the tangent line kind of hangs with it for a little while at least. So as long as you're right in this area right here really close to x equals 1, the tangent line's a good approximation. But of course, as you go out here far to the right or left from that, this logarithm curve is deviating from that line by quite a bit. Okay, and so that's our next thing. Our first degree Taylor polynomial approximation is a tangent line function. And certainly we can do better than a horizontal line. And the first degree polynomial function or linear function that best fits the graph near that point is again the Taylor is the tangent line. We want p of 1 to be a, p sub 1 of a, the value of this polynomial at a to be f of a. So it goes through the a f of a, and then we want that to have the same slope. Okay, so the first derivative should agree there. P prime of a is f of a. And so it turns out that P1 of x is f of a plus f prime of a times x minus a in parentheses there. So for our example, the derivative f of x is L log of x, f prime of x is 1 over x, and 1 over x evaluated at 1 is 1. So the slope is 1. So our tangent line is f of 1, which is 0, plus f prime at 1, which is 1, times x minus 1. So it's just x minus 1. And of course, that's the tangent line that you saw there. Once again, the tangent line gives a pretty good approximation of the original function if we stay close to the center point 1, 0. However, it deviates from the graph more and more the farther away we get from the center point. The graph above includes the zeroth degree polynomial for reference, the horizontal line, but we've improved the approximation considerably by increasing the degree of the approximating polynomial from 0 to 1. Okay. The point-slope form of the tangent line directly shows that the line goes through the point of tangency, and we can simply talk about polynomials centered at x equals a, which will have this form, the constant term, and then the sum from k equals 1 to n, whatever the degree is, of some coefficients, c sub k, times x minus a to the k. So this is going to be a polynomial expression centered at x equals a. Right? So it'll be c sub 0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed and so forth. We could rewrite this as just saying it's the sum from k equals 0 to n of c sub k x minus a to the k if we're okay with one little thing. When k is 0, the 0th term is x minus a to the 0, which is 1, times c sub 0, which is c sub 0. That all works out great, except when x is a, and then you got 0 to 0, which is undefined. So if you that's really an overstatement to reduce it to this last version here, but a lot of people do that, and we may do that from time to time. But if we do that, we have this caveat that we're going to assume that that expression on the right is just c sub 0 when x equals a. Okay, and k is 0. All right, so now let's move on to a second degree polynomial. So it's reasonable to assume that we could do an even better job of approximating the function if we could go up to a second degree polynomial. After all, a second degree polynomial has 3 coefficients for us to pick. C sub 0 plus C1 x times x minus a plus C2 times x minus a squared. A is fixed for us. In this case, it's 1. Okay, but what do we need to pick for these coefficients? So we need to get 3 pieces of information, characteristics of the formula and the graph, that we want to match. Well, the first and most important one is we want it to go through our center point. So P sub 2 of A has got to be f of A. Well, if you look at that, you put in A for x, that's 0, that's 0. So P sub 2 of A has to be C sub 0. So once again, this is just this C sub 0, whether it was the first one or the 0th one, the horizontal line, or whether it was the first degree polynomial or now the second degree polynomial, that c sub 0 is just f of a. Now we also would like the derivative to be there. So let's look at what we got. So here f of a is p sub 2 of a, which these are zeros, so this just c sub 0. So c sub 0 is f of a. That's what I just said. Now what about that? We want the derivatives to match too. We'd like the slopes to match there. Well, take a derivative. The derivative of the constant term is 0. Derivative of this term is just c. And we're basically doing a substitution. U equals x minus a. Du is just 1. Du over dx is just 1. So this is 2c2 times x minus a to the first power. All right, plug in x equals a. This term goes away. That's 0 there. And so you're just left with c1. So c1 is f prime of a. So once again, that c1 is our coefficient. That is our f prime of a. So far, the first part is exactly the tangent line, those first two terms. But then we have this quadratic term. So what's the natural next thing? Well, we'd like to get the concavity to match up as well. Well, that will mean the second derivative is the same. So the second derivative needs to match up. Okay, so the second derivative would be the derivative of this guy. Well, that's already gone. The derivative of that c1 is 0. And this would be just 2c2. So f double prime of a, we want to be the same as p2 double prime of a, which is just 2c2. So 2c2 needs to be f double prime. So divide by 2, you get c2 is 1/2 of f double prime. And so here's your second degree polynomial that's going to be the best fit. It's f of a plus f prime of a times x minus a plus 1/2 f double prime of a times x minus a squared. Notice that that's just the constant function, the horizontal line that best fit. These two terms make the tangent line, and then we add a third term to get the best fitting parabola. Okay, now I might want to actually start keeping track of some of this in a table. So n is 0. We'll say the zeroth derivative of a function is the function itself. So our original function was ln of x, that's the zeroth derivative. Evaluated at 1, you get 0. And our polynomial was just y equals 0. Then when we got the first derivative was 1 over x, or x to the negative 1. Evaluate that at 1, you get 1, and we get just x minus 1. The second derivative was negative 1 times x to the negative 2, or negative 1 over x squared. Evaluate that at 1, and that was negative 1. And what do we end up with? We get x minus 1, and we ended up with minus 1/2 x minus 1 squared. Let's see. Yeah, that should be negative 1/2. Let's see. Or is it positive 1/2? Let me look at this just a minute. The derivative, yeah, it's 1/2 the derivative. The derivative is negative 1. 1/2 of negative 1 is negative 1/2. So yeah, that's correct. That's all good. Now let's take a look at that in the app over here. Here's the second degree one. There's the x minus 1, and there's the minus 1/2 x minus 1 squared. I'll talk about that exclamation point there in just a minute. So look at what's happening here. This is a parabola here. This purple one here is the parabola. Notice that it meets the function right here. If I were to zoom in here really close, notice that the tangent line and the curve and the graph all are very close, but even the purple quadratic parabola is closer to the blue graph than the tangent line is. Now, of course, they both go further away, but that parabola is not only closer in close, it actually hangs with it longer, starts to significantly deviate a little bit further out than the tangent line. So that's a better approximation. So you gain in a better approximation, you lose because it's a second degree polynomial instead of first degree polynomial. So the approximating function got a little harder, but the level of approximation got a little better. Well, can we keep going? Well, sure, why not? Let's do a third degree polynomial, a cubic polynomial approximation. What would we want to do? We'd want all the derivatives the function of order 0, 1, 2, and 3, in other words, the function to match, and then the first, second, and third derivatives to match as well. So now our function looks like p sub 3 of x is c0 plus c1 times x minus a plus coefficient 2 times x minus a squared plus coefficient 3 times x minus a cubed. We want f of a to match, so when you plug in a, all these terms go away, and so c sub 0 once again is f of a. The first derivative, the derivative of the constant 0, you get c1, and this goes down once, so this becomes 2c2 times x minus a, and this becomes 3c3 times x minus a squared. Now plug in an a in place of this, all this goes away except for the c1, so c1 is once again f prime of a, because you want the derivatives to be equal. We want the second derivatives to be equal as well, so we need to do another derivative. Well, that's gone. Derivative of c1 is 0. The derivative here is 2c2. The derivative here is 3 times 2, or 2 times 3, and then x minus a. So we want the derivative of evaluated a to be the f double prime of a. We'll plug in a. This part goes away to 0, and you're left with 2c2. So f double prime of a is 2c2. c2 is 1/2 f double prime of a. This looks very familiar. This is exactly what we got when we were doing the quadratic approximation, right? But now we have a third term, so we do another derivative. That goes away to 0. And this last one is just 2 times 3 times, somewhere I lost a c3 right here. Let me put that back in. Okay, where is it? There it is. Right there. Okay. And I have it right there. Okay. And then when you plug in z, okay, we already did that part. So down here, do a derivative. You just get 2 times 3 times c3. And that's the third derivative. Or in other words, 6c3. But that needs to be the third derivative at a. That is the third derivative of p3. It needs to be the third derivative of the function. We want those derivatives to equal, right? So plugging it in, you get c3 is the third derivative at a divided by, well, 2 times 3, or 1 times 2 times 3, or 1/6, or you may remember that's 3 factorial. Okay, so anyway, this is f of a plus f prime of a times x minus a plus 1/2 f double prime of a times x minus a squared plus 1/6 f triple prime of a times x minus a cubed. So continuing our table one more down, we get this. And if you notice, we're just adding another term to what we did before. Here is the cubic version. Let's go back over to our app again. And here is the cubic polynomial. Once again, notice, see how it's hanging with the curve a little bit longer than the either the quadratic or the linear, or certainly better than the constant term, constant function. It's hanging with it closer and longer before it starts to really start deviating. Okay, that's interesting. How about a fourth degree one? Well, a lot of this is the same, so I'm going to zip through this quickly. P sub 4 of x is c sub 0 plus c1 times x minus 8 plus c2 times x minus a squared plus c3 times x minus a cubed plus c sub 4 times x minus a to the fourth. Plug in a is x equals a. All those terms go away, and c0 has to be f of a. Same as before. Do a derivative. First term goes away. Here you get c1, 2c2 x minus a, 3c3 x minus a squared, 4c4 x minus a cubed. Plug in x equals a. All those go away, and c1 has to be the same as f prime at a. c1 is. Do another derivative. Constant term goes to 0. This is 2c2. This is 2 times 3 times x minus a. This is 3 times 4 times c4 times x minus a squared. Plug in x is a, all those go to 0 except for the 2c2. 2c2 is f double prime of a, c2 is 1/2 f double prime of a. Same as before. Third one, same as before. Take another derivative. That first term goes away. You get 2 times 3 times c3. Then you get a 2 times 3 times 4, c4 times x minus a. Plug in x minus a here, a for x minus for x, and the a minus a is 0, so that term goes away. You got 2 times 3 times c3 is f triple prime of a. So the coefficient there, c3, is 1/6 f triple prime of a. That's all exactly like what we just did before. Now, when we do another derivative, the c3 term goes away, that constant term, and we get 2 times 3 times 4 times c4 times 1. And that is going to be the fourth derivative. But we want that to be the same as the fourth derivative at a. That shouldn't. All right, so the notation there is the superscripted power in parentheses. That's a derivative. Okay, so well, that's 24, or 2 times 3 times 4 times c4 is going to be the fourth derivative. So the c4 is the fourth derivative divided by 24, divided by 2 times 3 times 4. Here it is worked out for our particular one. The first part is going to be the same exactly as what we had before, but now this is 1/24th here when you do another derivative. So the next derivative down is negative 6x to the negative 4. Plug in 1, you get negative 6. But remember, that extra term is 1 over 2 times 3 times 4. You need to multiply those together. You get negative 6 over 24, or negative 1/4 for the coefficient. So there's the polynomial there. Let's take a look at it over here. So there's the fourth degree is that pink one. And notice right in here, it's even closer to the curve. They're all really close right in here. But as you get further out here, you can see that the fourth degree is better than the third, or the second, or the first, or the 0th one. Even in here where they're close, the fourth degree is going to be closer to the curve, except, of course, at the point where x equals a, then they're all perfect. Okay, now, have we done enough of these we can get a pattern going? Let's see. For every one, there are going to be n plus 1 terms, starting with the constant term and ending with the degree n terms. So they all look like this. And we can determine these coefficients. Well, the 0th one is always just f of a. And we want the derivatives to match all the n derivatives from 0 up to n. Okay? And each step, it turns out that if you could just figure out the n minus 1 polynomial, we just added an extra term. See here? It was 0, then we added this term, and to that we added another term, and to those two terms we added a third term, and those three terms we added a fourth term. So it's sort of recursively just adding on a new term each time. And that new term looked like c sub n times x minus a to some n power. But what was that c sub n? And basically when we're doing these derivatives, we're just using the power rule over and over and over and over again, along with the chain rule. U is x minus a, derivative of u with respect to x is 1, so chain rule didn't really add much of another factor of 1. But the product rule says that's n times u to the n minus 1. And if you do another derivative, well, let me finish doing the substitution. Derivative here is 1, so it's n times x minus a to the n minus 1. But every time we take a derivative, we're multiplying by the old power. So we have an n, then an n minus 1, then an n minus 2, and so forth. And you end up with all the factors up to n for that c sub n, that nth derivative. Well, we know that there's a shortcut notation for that, which is called n factorial. We've seen that before. So this is n factorial times c sub n, and that's the nth derivative at the, we want that to agree with the nth derivative at a. So the c sub n is 1 over n factorial times the nth derivative at a. So that extra factor in the coefficient is just 1 over n factorial, along with the nth derivative, of course. So here's our basic formula. It's f of a plus the sum from k equals 1 to n of k factorial on the bottom, and the top is the kth derivative at a times x minus a to the k. You can just leave this first term off and call this k equals 0 as long as you're willing to interpret the x minus a to the 0 as 1 even when a equals 1. And so here I've worked out the the fifth and the sixth ones here. And this one actually has a nice pattern to it. There's a nice pattern to the derivative here. It's always negative 1 to the n plus 1 times n minus 1 factorial, and you're dividing that by n factorial, okay? And so what's left is just 1 over n, or if they call the term number k, 1 over k, okay? So we're summing that up. So going back to our app, it will show the fifth and the sixth one separately. And again, each one is getting better. It will also do this. You can show the nth one by the slider and do this. Now, hey, it's doing it right now. Earlier I was doing this and I was having some problems when n equals 1, getting it to work right, but it seems to be working correctly now. This is showing you some information related to finding that last one. And so then I can look at it and I can see what's happening as I go further and further out. So here's the constant term, constant one, first degree, second degree, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, 18th. I can go all the way up to here's the 30th one. If you look at the 30th one, boy, it really, this part, it really does a really good job. In fact, it does a really good job right up to almost 2. And then beyond 2, it starts really diverging from that quite a bit. So this process seems to work really good between, say, 0 and 2. It seems to work out pretty well. Now, one of the things I can do is I can approximate this with, let's go back to 1. Remember, we did this, and we took a value, it could be anything we wanted. Let's just say 1.6. And here's a point on the curve. I can approximate it with the point up here on the curve up here, on the polynomial. Okay? And this will give it to you. And of course, it'll get better as I do this, get this better and better and better. Now this one, for that approximation to be pretty good, you may have to get n pretty big. But if that point is pretty close to this, like suppose I wanted to find the log, natural log of 0.9, that's pretty close. So I can approximate with these different polynomials. Look down here and you can see the approximations. And right now it's 0.109. That's just the zeroth approximate. It's 0 actually. And this is what my calculator or something would tell you would be. So negative 0.1 is approximation of 0.9. Now what is that? That's just taking that 0.9 and plugging it in this formula for the tangent function. Just 0.9 minus 1 is negative 0.1. Take that and plug it in this quadratic one here, that formula, and you get this. And notice now we're agreeing to 3 decimal places. Do it in 3, and now they're agreeing, they're going to at least 4 decimal places. 4, 5, 6. They're starting to agree further and further out. Looks like about the 9th one is about as far as my calculator would go. The 10th one, yeah, they're agreeing all the way out for however many digits this is that the, I think I've got this displaying 10 digits or something. Okay, so they're already agreeing that far out. If you wanted to agree further and further out, you could put more and more and more and more digits by doing more and more and more and more a higher degree polynomial. Okay, go back to the notes here. All right, so this is stuff I've already said. This is exactly what I did here. Approximate, say, with the 4th degree polynomial log of 0.9. The program worked this out in the background, but we can do it by hand here, put in 0.9 here. Now notice, you may not, without a calculator, how are you going to figure out what the natural log of 0.9 is? Well, here's one way. We know that this polynomial is the correct polynomial. We worked it out to degree 4. Put in 0.9. Well, 0.9 minus 1 is 0.1. It's negative. And we put that there in place. Of course, when you square it, those terms are going to be positive times that negative is negative. The odd ones are going to be negative, but they have positive out front. So it turns out all the terms are negative in the end. So that's 0.1. 0.1 squared is 0.01 times a 0.5, which is what that is negative 0.005. This is negative here. 0.001 times 1/3. That's 0.003 zeros, and then a 3 repeating, negative. Last one's also negative. That's 4 negatives, and one more negative makes 5 negatives. 1/4 is 0.25. Multiply by 0.0001. Lose a decimal 4 places to the left to get this. Add those up, you get negative 0.105353 with the 3 repeating. And with the calculator, you can get this worked out to be approximately negative 0.1053605,157. So it looks like, according to that, if this one is correct, this worked out 10536 rounds off, 10536 this rounds off negative. So this is good to 5 decimal places. So this would be one way you could have a calculator actually compute a logarithm, is to write a program that made it do this. Okay, and there's the point on the curve, and that's approximated by the corresponding point with the same x value on the pink 4th degree polynomial. Of course, we get an even higher polynomial, we get an even better approximation. This one is polynomial 10, which I'm not working out the details by hand here, but I worked it out with the calculator and the program, and it looked out to give us accurate to all 10 digits, which is the best number of places, say, a TI-84 does. Okay, let's try another one. Find the 5th degree Taylor polynomial approximation of f of x equals e to the x centered at a equals 0. We're going to use this polynomial to get approximate value of e. Compare this approximation to the one given by your calculator. Okay, well, the nice thing about e to the x is all the derivatives are just e to the x, and evaluate them at 0, they're all just 1. So this part of the table, super easy pattern for this. The k factorial here is 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, multiplied by 4 is 24, multiplied by 5 more is 120. And that's going to give us up to degree 5. So they're all just 1 over the k factorial, so it's just 1, 1, 1/2, 1/6, 1/24. And 1 over 120 are the coefficients, and there's your polynomial. So e is just going to be this evaluated at 1. So it's going to be approximated by this polynomial evaluated at 1, which is just adding these fractions up. I get a common denominator of 120. There it is, worked out. 326 over 120 is 163 over 60, or 2.716 with the 6 repeating, or to 3 decimal places, that's 2.717. And if you do it on your calculator, you get 2.718281828, which rounds out to 2.718. So we're only off by a 1 in the 3rd decimal place. And there it is there as well. Here I just did my same thing same application we were using a while ago. I changed the function of e to the x, changed the centering point to 0, and looked at n equals 5. I just slid this over to 5 and used the n by slider to give the red one, and then worked out that approximation. All right, here's another one. Find the smallest Taylor polynomial approximation with 4 non-zero terms centered at about a equals pi over 4. It's going to approximate f of x equals tangent of x. Do not use any known series but rather use Taylor's theorem directly showing all your computations. So in other words, do it like we just did. Now we might want to remember the trig values of pi over 4. Pi over 4, if you do it as a rotation angle from the standard position, you end up like this. And our little triangle is a right isosceles triangles with length side 1, 1, and square root of 2. If we put this in a circle of radius square root of 2. So that point is 1, 1. The radius is 2. X is 1, Y is 1. R is square root of 2. Theta is, or beta, I guess it is, as it is here, is pi over 4 or 45 degrees. Sine is Y over R, so it's 1 over square root of 2, or square root of 2 over 2 if you'd rather. Cosine is X over R, so it's 1 over square root of 2. Tangent is Y over X, so it's 1. And the reciprocals are what you get over here for cosecant, secant, and cotangent. All right, so just remember that little basic trig. Okay. I'm going to make a table similar to the table I used earlier. K is going to be 0, 1, 2, 3. And what did I say? Work out the first four non-zero terms. So the earliest I could hit is 3. If some of these turn out to be 0, then I might need to go up higher. The zeroth term, or zeroth function is the original function. Zeroth derivative is the original function, which is tangent of x. Plug in pi over 4, you get 1. Of course, k factorial is 1. 1 divided by 1, 1 for our coefficient. The root of tangent of x is secant square of x. Secant square of x, let's see, secant of x was secant of a, secant of pi over 4 was square root of 2. Square that, we get 2. 1 factorial is 1. 2 divided by 1 is 2. Second coefficient, or the first coefficient, really, the zeroth coefficient being 1. And then the first degree coefficient was 2. Now do a derivative here. So that's u squared, so that's 2u to the first, so it's 2 secant of x times the derivative of secant x, which is secant x tangent x. I combine the two secants together to be secant square. Plug in pi over 4, that's the square root of 2, then we square it to be 2, times that 2 is 4, tangent of pi over 4 is 1, so that's 4. 2 factorial is 2, 4 divided by 2 is 2 for the second degree coefficient. Now I need to do this, another derivative. I worked it out down here. It's the first, so it's 2 out front. Then I think of the product rule here. Secant square times derivative of the tangent plus tangent times derivative of the secant square. Derivative of tangent is secant square. Derivative of secant square is 2 secant of x, derivative of secant x, which is secant tangent. So let's see what we got. We got a secant to the fourth. We got a 2 secant square, and we got a tangent square there. I factored out a secant square out front with the 2, and that's left secant square of x plus 2 tangent square of x. Okay, well, anyway, I need to plug in pi over 4 in here. So secant of pi over 4 is square root of 2. Square that, you get 2 times 2 is 4. Again, we have a square root of 2 square there, and we have a 1 square there. So let's see, 1 square is 1 times 2 is 2, plus square root of 2 square is 2. 2 plus 2 is 4. 2 square root of 2 times square root of 2 is 2. So 2 times 2 times 4 is 4 times 4 is 16. 3 factorial is 6. You got 16 over 6, which reduces to 8/3 for our next coefficient. So our coefficients are just 1, 2, 2, and 8/3. And so, well, there it is. There's the polynomial. 1 plus 2 times x minus pi over 4 plus 2 times x minus pi over 4 squared plus 8/3 times x minus pi over 4 cubed. And this one is, again, using the same app that I had above. Here's the third degree polynomial approximating there. There's the point pi over 4 comma 1. And nearby it's pretty good, and not so good out further away. Okay, let's do one more, and we'll call it a day on this one. So find the smallest Taylor polynomial approximation with 5 non-zero terms centered at a equals pi over 6. And it's going to approximate the function f of x equals 3 sine x plus 2 cosine x. Again, use the method that we just did. Let me see if you can work this one out and come back and check your work. Please work it out yourself now. Press pause. We might want to recall the trig values of pi over 6. Power 6 is also known as 30 degrees. If you put this inside of a triangle of a circle of radius 2, then you have a nice little half of a equilateral triangle that fits in there. It has sides of ratio 1, 2, and square root of 3, and the angles are pi over 6, pi over 3, and pi over 2, or 30 degrees, 60 degrees, 90 degrees. Shows up all the time in trigonometry and calculus problems, probably more than it should, but it does show up a lot. And let's see, sine of this would be 1/2. Cosine would be square root of 3 over 2. Tangent would be 1 over square root of 3, and so forth. All right. The original function was 3 sine of x plus 2 cosine of x. Plug in pi over 6. Sine of pi over 6 was 1/2. Cosine of pi over 6 was square root of 3 over 2. 2's cancel here. Actually, I'm going to keep the 2 in the bottom. I get 3 plus 2 square root of 3 over all over 2. K factorial is 1, so it's just, that's your coefficient. 3 plus 2 square root of 3 over 2. Now do a derivative. Derivative of sine of x is cosine of x. Derivative of cosine of x is minus sine of x. So there's your derivative. 3 cosine of x minus 2 sine of x. Plug in pi over 6. Sine of pi over 6 is 1/2. Cosine of pi over 6 is square root of 3 over 2. Again, I just kept my common denominator of 2 for that. And I got 3 square root of 3 minus 2, or negative 2 plus 3 square root of 3. Dividing by 1 factorial, which is just 1. So it's negative 2 plus 3 square root of 3 over 2 is our coefficient of our linear term. Another derivative, derivative of cosine of x is minus sine of x. Derivative of sine x is cosine x. Plug in pi over 6. Sine of pi over 6 is 1/2. Sine of pi, oh, wait a minute, that should be, yeah. The derivative is negative 3 sine x minus 2 cosine of x. Plug in pi over 6. Let's see if I did that right. The cosine is square root of 3 over 2. The sine is 1/2. Yeah, the rest of it's worked out correctly. So that's a common denominator of 2. That's negative 3 minus 2 square root of 3. I just factored a negative out front and left both those terms positive in the top. So that's our thing. We divide that by 2. That's our coefficient. Negative, the opposite of 3 plus 2 square root of 3 over 4. Do another derivative. Derivative of sine is cosine. Derivative of cosine is minus sine. So it turns that middle term, or second term, back to positive. Evaluate at pi over 6. Sine of pi over 6 again is 1/2. Cosine of pi over 6 again is the square root of 3 over 2. So this is, what was a negative right here to begin with. So it's negative 3 square root of 3 over 2 plus 2 over square root of 2. So that's 2 minus 3 square root of 3 over 2. And then we're going to divide that by 6 factorial, or 3 factorial, which is 6. So that turns that denominator into 12. And we wanted 5 terms here, I think, so we want to do one more. Derivative of cosine is sine. Derivative of sine is cosine. If you notice, we're back to where we started, so we get the same thing right there. But this time we're dividing by 4 factorial, which is 24, so that denominator becomes 48. There's a pattern here that's going to cycle after every 4 times. That would help us working out a general term. But in any event, we just use those as our coefficients. There they all are. And so there's the polynomial. This is, after all, this is just a 4th degree polynomial. These coefficients are constants, even though they're a little somewhat nasty constants. Some of them got pi's on the inside. We got pi over 6. On the outside, we've got, some square roots in there. So anyway, there's our polynomial. And here's what the polynomial looks like. It's this red one here, and it hugs pretty close to the graph, at least in this region right in here for this particular one hump of it. Okay, so that is Taylor's theorem. That's how you do Taylor's polynomials. So Taylor polynomials give us great ways of approximating functions. So now you have an opportunity to go get you some homework done on this. Get some practice with this. See you back in a little bit.